am Satish Lele. This video is part of my chemical process piping channel on YouTube. This video is about types of coolant water, chilled water, and brine system. Open system. In the open coolant water system, all the required quantity of coolant water is withdrawn from the source sea, river, lake, or well water for entire plant coolant use. In this system, the water is drawn directly from the upstream side of the river, pumped through the condensers and then discharged to the downward side of the river at temperature 5 to 10 degrees centigrade in excess of the inlet temperature. The temperature of the discharged water should be kept within safe limits to prevent harm to fishes. The limit of discharged water temperature is specified by the Fisheries Board. The position of inlet and outlet should be chosen in such a way that there should not be any recirculation of hot water, which reduces the efficiency of the coolant water users. Therefore, the distance between the inlet and discharge points should be as large as 1 kilometer or more. This type of coolant water system can be used only when required quantity of water is available throughout the year. Plants on tidal waters using water from the tides or sea have a special problem in the construction of the coolant water system and in avoiding recirculation of the coolant water from the outlet back to the intake. In many plants, the intakes and outlets are separated by as much as 3 kilometers. In tidal waters, the water flows in one direction for some time and in another direction for some time. Therefore it requires special arrangements for the change in flow direction. Stations taking water from river or tidal sources usually have the ends of both suction and discharge pipes submerged below the lowest recorded tidal level. The water circulation system will operate at all times and at all states of tide if the distance between the lowest level and highest point of the circulation water system exceeds 1 kilometer. In many plants, intakes and outlets are separated by as much as 3 kilometers. Closed system. The recirculating or closed coolant water systems operate in a closed loop with fresh water makeup which constitutes only a small fraction of the coolant water circulation. Closed systems are of two types: water or air-cooled type. It employs coolant showers or coolant pumps. A coolant type employs direct dry type coolant shower system or indirect air coolant system. When enough quantity of water is not available for coolant requirements from rivers, the closed type system is universally adopted. In the closed system, the hot water coming out of the coolant water users is cooled either by splashing in the pond or passing through the coolant shower instead of discharging to the downward flow of the river. The quantity of water required is from the river during flood periods or when sufficient water is available with required purity, and same water is used again and again for condenser by passing through the coolant showers. Mixed system. The combination of the one-through and recirculating or mixed coolant water system is sometimes employed to carry out process cooling via the closed coolant water, which in turn is cooled by an open coolant water circuit in a suitable heat exchanger. The main advantage in this system is the flexibility of operation it gives to the process side, which is on the closed loop. Another type of mixed system uses river water as well as the coolant shower simultaneously. This system overcomes the difficulty of recirculation and meets the requirements of the Fisheries Board on a fairly small river. A part of the water from the coolant water users is discharged directly into the downstream of the river, and part of the water is pumped to the coolant shower, where it is further cooled and then discharged. downward side of the river. In this way, the water discharged to the river is maintained at a suitable temperature and recirculation troubles are eliminated. The advantages of this system are: the size of the cooling towers can be reduced where the site area is limited. The quantity of cooling water required is reduced as the recirculation is eliminated. The turbine plant efficiency is increased. This system should be adopted only when there is a possibility of recirculation and it is necessary to meet the requirements of Fisheries Board. Cooling towers. There are two types of cooling towers: natural draft and induced draft. Cooling towers are heat removal devices used to transfer process waste heat to the atmosphere. Cooling towers may either use the evaporation of water to remove process heat and cool the working fluid to near the wet bulb air temperature, or, in the case of closed-circuit dry cooling towers, rely solely on air to cool the working fluid to near the dry bulb air temperature. Natural draft cooling tower. The natural draft or hyperbolic cooling tower makes use of the difference in temperature between the ambient air and the hot air inside the tower. As hot air moves upwards through the tower, because hot air rises, fresh cool air is drawn into the tower through an air inlet at the bottom. Due to the layout of the tower, no fan is required and there is almost no circulation of hot air that could affect the performance. Concrete is used for the tower shell with a height of up to 200 meters. These cooling towers are mostly only for large heat needs because large concrete structures are expensive. There are two main types of natural draft towers. Cross-flow tower. There is drawn across the falling water and the fill is located outside the tower. Counterflow tower. There is drawn up through the falling water and the fill is therefore located inside the tower, although design depends on specific site conditions. Common applications include cooling the circulating water used in oil refineries, petrochemical and other chemical plants, thermal power stations, and HVAC systems for cooling buildings. Cooling towers vary in size from small rooftop units to very large hyperboloid structures that can be up to 200 meters tall and 100 meters in diameter, or rectangular structures that can be over 40 meters tall and 80 meters long. The hyperboloid cooling towers are often associated with nuclear power plants, although they are also used to some extent in some large chemical and other industrial plants. Although these large towers are very prominent, the vast majority of cooling towers are much smaller, including many units installed on or near buildings to discharge heat from air conditioning. Mechanical draft cooling tower. Mechanical draft towers have large fans to force or draw air through circulated water. The water falls downwards over fill surfaces, which help increase the contact time between the water and the air. This helps maximize heat transfer between the two. Cooling rates of mechanical draft towers depend upon various parameters such as fan diameter and speed of operation, fill for system resistance, etc. Mechanical draft towers are available in a large range of capacities. Towers can be either factory built or field erected. Concrete towers are only field erected. Many towers are constructed so that they can be grouped together to achieve the desired capacity. Thus, many cooling towers are assemblies of two or more individual cooling towers or cells. The number of cells they have, e.g., the 8-cell tower, often refers to such towers. Multiple cell towers can be linear, square, or round depending upon the shape of the individual cells and whether the air inlets are located on the side or bottoms of the cells. Components of a cooling tower. The basic components of a cooling tower include the frame and casing, film, cold water frame and casing. Most showers have structural frames that support the exterior enclosures, casings, motors, fans, and other components. With some smaller designs, such as some glass fiber units, the casing may essentially be the frame. Wooden towers are still available, but many components are made of different materials, such as the casing around the wooden framework is glass fiber, the inlet or louvers of glass fiber, the fill of plastic, and the cold water basin of steel. Many towers, casings, and basins are constructed with galvanized steel. Where corrosive atmosphere is a problem, the tower and or the basin are made of stainless steel. Larger towers sometimes are made of concrete. Glass fiber is also widely used for cooling tower casings and basins, because they extend the life of the cooling tower and provide protection against harmful chemicals. Film. Most towers employ films made of plastic or wood to facilitate heat transfer by maximizing water and air contact. Plastics are widely used for fill, including PVC, polypropylene, and other polymers. When water conditions require the use of splash fill, treated wood splash fill is still used in wooden towers, but plastic splash fill is also widely used. Because of greater heat transfer efficiency, film fill is chosen for applications where the circulating water is generally free of debris that could block the fill passageways. There are two types of film. Splash fill. Water falls over successive layers of horizontal splash bars, continuously breaking into smaller droplets, while also wetting the fill surface. Plastic splash fills promote better heat transfer than wood splash fills. Film fill consists of thin, closely spaced plastic surfaces over which the water spreads, forming a thin film in contact with the air. These surfaces may be flat, corrugated, honeycombed, or other patterns. The film type of fill is the more efficient and provides same heat transfer in a smaller volume than the splash film. Cold water basin. The cold water basin is located at or near the bottom of the tower, and it receives the cooled water that flows down through the tower and film. The basin usually has a sum or low point for the cold water discharge connection. In many tower designs, the cold water basin is beneath the entire film. In some forced draft counterflow design, however, the water at the bottom of the fill is channeled to a perimeter through that functions as the cold water basin. Propeller fans are mounted beneath the fill to blow the air out through the tower. With this design, the tower is mounted on legs, providing easy access to the fans and their motors. Mist eliminators. These capture water droplets entrapped in the air stream that otherwise would be lost to the atmosphere. These are located at top. Air inlet. This is the point of entry for the air entering the tower. The inlet may take up an entire side of a tower cross-flow design or be located low on the side or the bottom of the tower counterflow design. Louvers. Generally, cross-flow towers have inlet louvers. The purpose of louvers is to equalize airflow into the fill and retain the water within the tower. Many counterflow tower designs do not require louvers. Spray nozzles. These spray water to wet the fill. Uniform water distribution at the top of the fill is essential to achieve proper wetting of the entire fill surface. Nozzles can either be fixed and spray in a round or square patterns, or they can be part of a rotating assembly as found in some circular cross-section towers. Plastics are also widely used for nozzles. Many nozzles are made of PVC, ABS, polypropylene, and glass-filled nylon. Fans. axial propeller type and centrifugal fans are used in towers. Generally, propeller fans are used in induced draft towers, and both propeller and centrifugal fans are found in forced draft towers. Depending upon their size, the type of propeller fans used is either fixed or variable pitch. The fan with non-automatic adjustable pitch blades can be used over a wide kilowatt range because the fan can be adjusted to deliver the desired airflow at the lowest power consumption. Automatic variable pitch blades can vary airflow in response to changing load conditions. Aluminum, glass fiber, and hot-dipped galvanized steel are commonly used fan materials. Centrifugal fans are often fabricated from galvanized steel. Propeller fans are made from galvanized steel, aluminum, or molded glass fiber reinforced plastic. Location of coolant towers. Locate coolant towers downwind of buildings and equipment to keep spray from falling on them. Orient the short side of the tower into the prevailing summer wind for maximum efficiency. This means that the wind will travel up the long sides and be drawn into both sides of the coolant tower equally. When the wind is allowed to blow directly into one long side, it tends to blow straight through and results in lower efficiency. Locate coolant towers a minimum of 100 feet or 13 meters from process units, utility units, fire equipment, and process equipment. Chilled water and brine system. These are recirculating or closed chilled water systems operate in closed loop with fresh coolant of chilled water or brine. In case of brine, 3 chemicals used for brine solution: sodium chloride or common salt, calcium chloride, and ethylene glycol. Sodium chloride brine is highly corrosive but highly soluble. It is very cheap and very effective. It can reach a temperature up to -10 degrees centigrade. It is mostly used in ice manufacturing plants. Calcium chloride brine is less corrosive but less soluble. It is big, expensive, and less effective. It can reach a temperature up to -10 degrees centigrade. It is mostly used in chemical plants. Ethylene glycol brine is least corrosive and highly soluble. It is expensive and very effective. It can reach a temperature up to -30 degrees centigrade. It is mostly used in chemical plants. Chilled water has no additives. It has not much corrosion. It is cheapest of all. It can reach a temperature up to 5 degrees centigrade. It is mostly used in chemical plants. In chilled water or brine system, basic equipment are chilled water tank, chilled water pump, chiller and process plant, refrigeration unit, which are of 2 types: water-cooled or air-cooled. Thanks for learning. If you like this video, please give a like to my channel and subscribe it.